Howdy guys, we will start our last lab this week. It is lab 9 and we will design the single cycle processor, and we will use all the modules we designed in the previous two labs and connect them in by this following this diagram and make it a single cycle processor. And in question 1, we will design another module which is a single cycle control, and it is pretty easy. And if you have passed all the if you got the full credit for the last question in the pre-lab. And so this is the single cycle control. So for each opcode, yeah, we will just assign these signals based on the pre-lab table. So before you complete this lab, you need to make sure you got 10 of 10 for the last question in the pre-lab. Okay, so for the question 2, we will design the single cycle processor, and we have a sample template for that, and we will we need to connect all the modules based on this diagram, and I will explain some code inside. So for this, actually, this is a 2i max. Rn, it is if reg log is 1 and Rn will equals to instruction 0 to 4th bit, and if reg2 log is 0, Rn will equals to instruction 16 to 20 bits. And in this diagram, we will have some 2-1 multiplexer. You can design that based on this format. If you want to connect the two modules, actually, maybe for the instruction memory, where is that? Yeah, this is the instruction memory, and the data and address should be the var name inside the instruction module. You can see that is data and address, and inside the parentheses, it should be the intermediate var name in the diagram, and this var should be the instruction var will connect to the data input, data output, and current PC. This var will connect to the address, the input of instruction memory. This is how we connect the modules. Just make sure the you have the var names, intermediate var names, and connect to the corresponding input or output. And this is for the single cycle control, and we have provided the name for that. And what you need to do is to connect the remaining data path elements, and we also provide the we also provide the source code for the instruction memory and data memory. And so for question 2 and question 3, you can just consider them as a same question, because when you design the single cycle processor, you also need the modules, instruction memory, and data memory. And you can ignore this line because in the previous semesters, we will design data memory by ourselves and replace the previous one. But now we don't design the data memory, so just use this source code and connect them in the diagram. And actually, when you run the simulation, we have the test bench, and we only have one test case inside. So all you need is to get it passed. And actually, it will take you a long time if there is something wrong, because it is very hard to debug that. And so I suggest you to read the instruction memory, because you will also need to do that in question 4 and question 5. Okay, so in the instruction memory, yeah, these instructions are be read to the single cycle processor. And first you need to encode it, these instructions, and encode it to compiling language to make sure you understand what this instruction is doing. And in the question 4, we will add a new instruction MUSI, and we will also need to write how to implement question 5 into the instruction memory. Okay, we will talk about this later. So for the question 4, when we add the MUSI instruction, and we need to first know what is MUSI. And in the ARM, this is the MUSI, and I think you can also find it in the textbook. It's move a shifted 6-state base intermediate to the register, which is similar to the left shift, logical left shift. Yeah, sorry. And what you need to do is to specify some changes to the control and data path. And when you add the MUSI function, you need to add MUSI to the single cycle control. And for the MUSI, the instruction, you can find that in the textbook green sheet. Okay, and you can find the MUSI here, and we also provide the opcode for that. So you need to add the opcode to the single cycle control. Yeah, just like that. And you also need to get all the signals table for the MUSI function and add it here. That is for the single cycle control change. And you also need to add a LSL operation inside the ARU, because MUSI is very similar to that. So we will implement the MUSI by using LSL operation. And we also need to change the sign standard, because for the MUSI, the type of instruction is different from the 4 instructions we designed before. So we need to add one more instruction sign standard in the sign standard. And the control we used to have is 3 bits, but now we will make it 3 bits to allocate another instruction. And in Lab9, after you have changed the control and data path in question 4, we need to edit the instruction memory. Yeah, we will implement to construct a constant from 1 to 3, 4, 5, A, B, C, E, F, and save it in the register X9 first. And I can give you some hints. For the MUSI, it will just shift left by 16 bits each time and save it into a register. So each time you can you will move 4 bits in hex into the register 9, and so it is 64 bits in total. So we need to use MoveZ for four steps to construct this constant, and we will store this immediate value to the memory at memory address 28 and load this value back to the register X10. And to understand how to do that, you need to encode these instructions first. Actually, it is very I think I remember it is similar or the same to the last several instructions. So if you have encoded these instructions, you will know how to store the immediate and load it back. After you add the new instructions for the MoveZ in the instruction memory, you also need to add one more test in the single cycle processor test batch file to add one more cycle to output the result to test your cases, to test your source code. Okay. Okay. Oh, sorry, I forgot one. So before in the sign standard, you design the sign standard with an input of 26 bits, and so but for the 26 bits, it is the last 26 bits of the instruction, and the control signal is decided by the opcode. So before you implement the sign standard, you had better add a new module to make it get the output of the control signal, which is decided from the opcode, which is the instruction, the first 11 bits of the instruction bits, so that we can know which type of the instruction we want to extend. Okay, that's all. And for the Lab9, it is hard, and it's harder than before. So I suggest you start this lab as early. Yeah, just yeah, good luck with our last lab. Yeah, thank you.